Hello and welcome. Today we want to show you a new over-the-air hardware-in-the-loop validation solution for the test of automotive radar sensors. The solution consists of the Vector virtual driving platform and the Rode and Schwarz radar test system. With me in the studio today is Tobias Oeser from Vector and myself, Alois Ascher from Rode and Schwarz. So let's directly start with the topic. So what is the current situation when talking about radar-based autonomous driving? If you have a look at that picture, you can obviously see that more and more radar sensors are installed into the vehicles. They are used for different kinds of applications, so for cross-traffic assistance, park assistance, and even safety critical functions like emergency braking. One of the key challenges is that all those systems have to be reliably and reproducibly tested in the lab before validation and certification of each of those functions into new cars. With this testing need, several test challenges are occurring. So what is the situation with respect to those challenges? There is the limitation of current laboratory test options. What does that mean? Over-the-air sensor stimulation is currently missing in a reliable and reproducible way. We have only limited scenario testing capabilities, which are broadly available. And a very important part is that azimuthal movement of targets is currently very challenging to simulate. So current solutions rely on mechanical movement of the antenna front ends, but those movement is critical in terms of reproducibility and also reliability. Open and closed loop testing capabilities like combined solutions are missing. And the interfaces for hardware-in-the-loop applications are often not really open. So there are limitations due to the design of several hardware suppliers. And then obviously a combined, coordinated and overall user-friendly solution is not available, but is required by the market. Why is this so important? Reproducible and standardized testing is getting more and more important. There are currently millions of test kilometers that were driven with vehicles shortly before they come to market. And during that millions of test kilometers, corner cases are identified. And those corner cases, which show some unwanted behavior, for example, of an ADAS feature, are currently challenging to reproduce. And there is obviously a need for that. And of course, there is an increased number of ADAS capabilities that are coming or installed into new vehicles that come to the market. So now let's have a look onto hardware-in-the-loop validation of automotive radar sensors and the solution that we want to showcase to you today. So let's start with a short system overview. So the key components of the system is, on the one hand side, the Rode and Schwarz radar test system, as already mentioned, and the Vector virtual driving platform. The Vector virtual driving platform, in our case, consists of Canoe and Dyna4. Dyna4 simulates the environment or the objects, the artificial objects, and streams out the object data using the Open Simulation Interface, so the OSI format. Those data is streamed into the AREC 800A, which is the backend of the radar test system, which is generating the artificial objects. The ARIC 800 then generates those objects and streams it out to the QAT100. The QAT100 is the front end of the radar test system, which is simulating the azimuthal movement of the artificial objects. Then the objects or the scenery is provided over the air to the radar under test. And the radar under test, in the end, streams its object list via CAN bus to Canoe, back to Canoe, which then performs a result validation between simulated scenario and the received or recognized objects that are streamed out via the CAN bus interface. But now, let's first of all focus on the hardware parts, so the actual radar test system. In front of me here on the table are the two main components of the Rohde & Schwarz radar test system. The one I already mentioned, the ARIC 800A, the automotive radar echo generator, which acts as backend of the radar test system for moving object stimulation. The second part, the QAT100, the advanced antenna array, which acts as front end and is more or less simulating the objects from the azimuthal directions where the objects should appear for the radar sensor under test. So what are the key features when we talk about the Rohde & Schwarz radar test system? First of all, of course, for hardware in the loop, so open loop or closed loop test cases, the generation of dynamic echoes is necessary. Then, what's also very important is that we have the possibility or capability to simulate multiple objects in an independent manner. So with the ARIC 800 and the QAT100, we have the possibility to simulate up to 8 individual artificial objects that appear with individual radar cross-section, distance, radial velocity, and azimuth. What's also very important when we talk about how future-proof a system is the high instantaneous bandwidth that we support. So with the QAT100 and the ARIC 800, we are able to stimulate radar sensors with up to 4 gigahertz of instantaneous bandwidth. The whole setup, so front end and back end, are performance optimized, which means that they are developed together, and for the user, they are not two individual boxes, but they are controlled and seen as one box, as a one-box solution. So the QAT100 is fully controlled by the ARIC 800. The setup is also fully scalable. That means we do not only have the setup like we have it here in the studio with one ARIC 800A and one QAT100, but if the scenario requires it or the application requires it, we can use multiple front ends, for example, to cover a wider field of view for the radar sensor under test. Or we could also use multiple ARIC 800As if more artificial objects are required to be generated. And as already mentioned before, we support we have a seamless integration to the hardware in the loop test environments via open simulation interface. So when we talk a little more about scalability and flexibility of the ARIC 800A. So as you can see here on the picture, the ARIC 800A can be connected with several QAT100s. In this case, for example, one can have a combined testing either of multiple radar sensors, or one could also have a solution where we can cover a wider field of view. So that means, for example, if the long-range radar in that case does not only support a long-range mode, but also has the possibility to switch to a short range or mid-range mode, which typically requires a larger field of view. If a certain scenario needs to be simulated, then we have the open simulation interface connection to the simulation environment, which is in the case of the setup we want to show you today, the vector virtual driving platform. And that is also the next point where we want to talk about the integration of the vector virtual driving platform together with the Rohde and Schwarz radar test system into an harmonized and combined solution. And therefore, the second part is still missing. So I would like to hand over to Tobias and to ask him to give us a little more insights into the vector solution.
Thank you very much. For this setup, we need to provide radar detections from the virtual sensor, and we want to receive the CAN messages from the real sensor. The latter is the ideal task for our tool Canoe, which is the tool for developing, analyzing, and testing ECU networks as well as individual ECUs. To provide the virtual radar detections through the Hill API of the Rohde and Schwarz backend, we need sensor models. And not only for sensor, but also for vehicle under test and also for surrounding traffic participants. This is where Dyna4 comes into play. It contains such physical models and lets you create scenarios for virtual test drives. And to use Canoe as the execution environment, the model can be exported from Dyna4. In our setup, the compiled Dyna4 simulation model directly communicates with the Rohde and Schwarz backend using 0MQ as message queue and the open simulation interface as interface specification. To analyze the available data, the CAN detections are mapped to predefined Canoe objects, and the ground truth from the Dyna4 simulation model is directly transmitted to Canoe, again relying on standardized messages according to the open simulation interface. Once the data is available in Canoe, it can be used with the common Canoe analysis and test features. Here we are visualizing the ground truth objects and the detected objects from the real sensor in the scene window. In this way, you can easily compare the output of the real sensor with the simulation input. Let's have a look directly at the tool. This is the Canoe main window, where you can control the entire measurement. We are using a compiled Dyna4 simulation model that is embedded into the Canoe simulation setup. Therefore, we can also control the scenario simulation from Canoe. And this includes not only basic controls like start, stop, and reset, but also the selection of different scenarios or vehicle parameters. And of course, these actions can easily be automated either within Canoe or from any external tool. On the left side, we are using Canoe's scene window. The scene window shows the simulated objects from Dyna4 as blue bounding boxes. These represent the ground truth because they are the exact positions that Dyna4 calculates in the virtual world. The real sensor outputs from the CAN are visualized as green bounding boxes in this picture. The overlay provides a quick feedback whether the detection is properly simulated and the sensor functions behave as expected. As expected, the bounding boxes match well here. The right side shows the Dynanimation tool. This provides a 3D animation of the scene. It receives the movement data directly from the Dyna4 model running in Canoe. And it provides a live visualization. In this animation window, you can move around, focus on other targets, change camera position, and so on. And Dynanimation is part of Vector's virtual test drive solution called Dyna4, which we will have a look at closer now. Virtual test drives require models to reflect the real-world physical behavior. But for ADAS functions, actually a variety of models is necessary, because we are not only interested in a single vehicle, but also in the surrounding of that vehicle and the environment. Nevertheless, we do need a detailed model for the vehicle under test. In our case, to create a realistic motion of the sensor carrier. And such a model also enables realistic closed-loop vehicle reactions, like if the vehicle needs to perform an emergency braking triggered by an ADAS function. Once we have the vehicle, we need an environment. Starting with this static environment, which contains the road network with lane marks, surrounding terrain, buildings, and also environmental conditions like light and weather. Besides this static part, obviously, other traffic participants that interact with each other and the vehicle under test are required to reflect the dynamic environment. Now that the vehicle under test can drive in a virtual environment, we have to sense this environment. To this end, we need sensor models that provide virtual sensor data to stimulate functions, algorithms, real controllers, and so on. Depending on the use case and the interface, this data can range from ideal object lists to complex physical raw data like point clouds. Dana 4 provides predefined and parameterizable models for all of these domains. And similar to the sensor models, all of these models, depending on the use case, provide different fidelities. For example, a multi-body vehicle with detailed axle models, or a simplified single-track vehicle dynamics model, which requires less parameters. However, there's one last requirement to mention: an easy interfacing to the system under test. The Dyna 4 models are based on Simulink, which makes extensions very simple. This can be done via existing Simulink models, C or C++ code, FMUs, co-simulation interface, and so on. In this project, for example, a custom C++ S function provides the 0MQ message transmission to the Rode and Schwarz system. And this flexibility is not only limited to pure software tests, as Dyna 4 models can also connect to real ECUs. As you know, for this project we use Canoe, but Dyna 4 supports multiple real-time systems for signal exchange and execution. And now, let's have a direct look at the tool in our live demonstration. Here we have a look at the Canoe main window. On the right side, we see the Dyna animation window, where we have a visualization of the scene. It's a simple rural driving scene with some vehicles, some of them in front of our vehicle, and also some oncoming vehicles. After the oncoming vehicles have passed, there's an overtaking from the other traffic participant, and finally from the vehicle under test as well. The ground truth information from Dyna 4 is sent to Canoe, which is visualized on the left side in the scene window, where you have these blue bounding boxes. Furthermore, the radar detections are sent through an Ethernet cable to the Rode and Schwarz REC 800A. And finally, Canoe is connected to a CAN line and a CAN interface, which receives the radar detection from the real sensor. These detections are mapped and visualized as green bounding boxes in the scene window on the left side.
So thank you, Tobias, for showcasing the setup. Now, let's have a summary of everything what we have seen today. So the Vector virtual driving platform and the Rode and Schwarz radar test system form a fully harmonized solution, which can be used in combination to address various open loop and closed loop test cases. The setup can be adjusted regarding your test needs and test applications, thanks to its flexible and scalable concept. And precise and repeatable measurements are possible thanks to the QAT100, which allows electronical control of the artificial object directions. So this brings me to the end of today's presentation. Tobias and I, we say thank you for attending and see you next time.